Alright guys, so I had a few requests for more examples for related rates problems. So related rates problems, are a struggle for most students, but they're a direct application of implicit differentiation. If you want a lot of examples and more explanation, check out my full length lecture video on related rates. You can find it on my channel on YouTube. But here I'm going to work out some examples. I'm going to start off with some really easy and work towards harder ones. So the basic idea is that you have a couple variables, usually two in this case, but we might have more that we have to maybe condense down to two variables, and they're all changing at different rates, and we want to figure out, how one is changing under a certain scenario. So just a very basic example. Let's look at this one I have written here. It says let y be defined by 3x squared minus 5x. So we have a function. Typically with a related rates problem, that's probably the hardest part to come by, because you have to figure out from 3 or 4 sentences what your equation is. But let's just start off really easy, and we're given an equation. So we have y's, we have x's. And the directions say find dy dt when dx dt is 2. That is, we want to figure out how y is changing with respect to time when x is changing with respect to time at a rate of 2. Now that 2 is meaningless. There's no units on it. It's not meters per second or radians per hour. No, there's no context here. But the idea is still the same. X is changing at some rate, and we want to find how y is changing when x is changing at that rate. Oh, and I noticed I left off something we need. I realized that the next step I'm about to need another piece of information, and we need, let's see, x equals 3 will work. So, and let's see, let's fix this. And x equals 3. All right, left off part of the problem. So, we have a scenario, dx dt equals 2 and x equals 3, and we want to figure out dy dt when that happens. Now, the basic step, once you have your equation, is to differentiate both sides of the equation with respect to t. That's very important. So this section is covered right after implicit differentiation, where we were taking the derivative of both sides with respect to x. Here we're taking the derivative of both sides with respect to t. So let's take a stab at this. So we want to work with this equation here. If we take the derivative of a y with respect to t, all we get is dy dt. It's like you take the derivative of a linear variable, you get 1, but since it's a function of y and we're taking the derivative with respect to t, we have to write dy dt. All right, let's see. So the derivative here would be, what, 6x. But since we're taking the derivative of an x term with respect to t, we have to multiply by dx dt. Okay, and we have minus 5x, so the derivative is going to be minus 5. But again, we took the derivative of a x term with respect to t, so that's dx dt. Okay, so now we have differentiated both sides of the equation, and this is the point where you just plug in all of the stuff you know and solve for that thing you don't know, which is dy dt. We're looking for dy dt, and let's look what we're left with. We know what x is, we know what dx dt is, and we have 2 instances of dx dt. So now we can simply say that dy dt is 6 times x, which we said was 3. So 6 times 3 times dx dt, which is 2. So 6 times 3 times 2 minus 5 times dx dt, which is 2. So what we get? We get, let's see, 6 times 3 is 18 times 2, so what, 36? 36 minus 10 equals 26. Okay? So that's it. Y is changing at a rate of 26 something whenever x is 3 and x is changing at a rate of 2 something. Whatever those rates are, whatever the context is, doesn't make a difference at this point. But that is the basic idea of a related rates equation. Okay, again, I want to stress this is typically the hard part, getting that. Okay, but let's start with, or let's move on to one that's not so hard, and we'll progressively get a little more difficult here. All right, let's see. We have, all right, the edges of a cube increase at a rate of 2 centimeters per second. How fast is the volume changing when the length of each edge is 50 centimeters? All right, well, notice some keywords here, volume and cube. All right, so we're talking about the volume of a cube, and what's the volume of a cube? So you need to have some of these basic formulas in the back of your head. You know, it's not a lot to ask for you to know how to find the volume of a sphere, the area of a triangle, the area of a square. You know, these basic geometric formulas you've been working with for probably 10 years at this point. So we know that the volume. Let's define a variable. Let's say let x equal the edge of a cube. Okay, so if x is the edge of a cube, and by the way, there's nothing special about x here. You could have used s for side or whatever. Do be careful if you're working in your online homework. Your online homework may request you to use a specific variable in some cases. Like if you have to write out your related rates equation as a part of your answer, you may need to use a specific variable. But I'm going to use x here. I'm not doing my online homework right now. Let's just let x be the edge of a cube. So volume is what then? Well, to find the volume of a cube, it's all of the edges are the same length, and it's area of the base times the height. So it's x times x times x, otherwise known as volume equals x cubed. That's how you find the volume of a cube. Pretty basic, okay? All right, so let's see. What do we know here? It says the edges of a cube increase at a rate of 2 centimeters per second. So if x is the edge of a cube, I know it's expanding, so it's going to be positive. So it's the rate of change, that is dx dt, with respect to time, is 2 centimeters per second. Okay, so dx dt equals 2 centimeters per second, and I want to know how the volume is changing when x equals 50 centimeters. Now here's the thing, I'm not plugging in a 50 right away. That's not going to help me any good. That's just going to find the volume when the edges are all 50 centimeters. I want to know how fast the volume is changing. So another key thing about related rates equations is you don't just start plugging in variables. You know, I am going to eventually plug in when x equals 50, but I don't do that right away because that's not helpful at all. It's not answering the question. I don't have any derivatives yet. Derivatives are all about rates of changes. I don't have any derivatives yet, so I can't start plugging in. But I'm about to, because I'm about to take a derivative. So once I have this equation here, I have my initial conditions, and then I go here and I say, all right, well, what's the derivative of both sides with respect to time? Well, on the left-hand side, we just get dv dt. On the right-hand side, we get 3x squared, but again, I took the derivative of an x term with respect to time, so dx dt is required. Okay, at this point, hopefully, if I've defined these constraints over here appropriately, or maybe these conditions, not constraints, I should be able to plug in and solve for what I don't know. Okay, so I'm solving for how fast the volume is changing. That's dv dt, change in volume with respect to time. This is change in edge with respect to time. So and this one is conveniently solved for what I'm looking for. That won't always be the case. Sometimes you might be solving for dx dt and you know dv dt, and so you'll have a little extra algebra to work with. But this is already set up pretty nicely for us, because all we need to do to find dv dt, how fast is volume changing, is to simply plug in these things we know about. So let's see, we have a 3. X is going to be 50. So 50 squared times dx dt, which is 2. Okay, so let's see, 3 times 50 squared times 2, so 6 times 50 squared, I get 15,000. Okay. But let's not forget our units here. Let's see, so 15,000, we're talking about the volume changing. And what is our time like, okay, per second, okay? So we're talking about volume changing, so volume is in cubic units, so it's centimeters cubed per second, since that's our time measurement. So you don't want to leave off your units, clearly. That's probably your elementary and junior high teachers told you that all the time. Don't ever leave your units off, because 15,000 is kind of meaningless without some sort of units when you're working in an applied setting. So if your volume is always going to be measured in cubic units, length is always going to be measured just in regular. If we were talking about length, it would just be centimeters. If you're talking about area, it would be centimeters squared, square centimeters. So just always keep that in mind. All right, so there we worked from really easy to a little bit harder. Now let's go a little more difficult. Okay, these are going to increase in difficulty a little bit. So let's see what's going on here. All right, so let's see. This is a pretty classic problem. In my other video, if you watch that, you'll see we talk about a falling ladder problem. That's another classic problem. There's a handful of these just really classic. Every calculus textbook is going to have these problems, and this is one of them. Moving shadows. It says a 5-foot-tall woman walks 8 feet per second toward a street light that's 20 feet above the ground. What is the rate of change of the length of her shadow when she's 15 feet away from the street light? At what rate is the tip of her shadow moving? Now, sometimes your textbook is nice and gives you a picture. Sometimes it doesn't. In this case, there's no picture, so we need to draw a picture. So let's see. Let's see here. We need to draw what's basically going on here. So we have a street light. That's the easy part. So a street light up here. Light. Okay, street light. And let's see here. It's 20 feet above the ground. So 20 feet. Okay, let me back that up a little bit. 20 feet, so we can see. All right, so we have a street light that's 20 feet above the ground. All right, and let's see. She is 15. Well, eventually she's gonna be 15 feet away from the street light. So what does this look like? Let's draw this. There's the ground. And you have a person that's 5 feet, a woman that's 5 feet tall. Okay? So let's see here. Let's just go like that. Obviously, this is not drawn to scale. 5 feet. So we have a person here, obviously that's just represented by a line, a street light here. Now, what does the shadow look like? Okay, if you have rays of light going off in every direction, those rays of light are going to hit this person, be blocked by her, and hit the ground. The shadow is going to be like this. Okay, so we have, these rays of light coming like this. And her shadow is going to be this distance right here. Okay? This little the base of this little triangle is going to be her shadow. Okay? Because there's going to be light over here, maybe light over here, but maybe blocked in this case. Okay, so this is basically what's going on here. Now let's see, is there any kind of information we know? Eventually we're going to talk about when she's 15 feet away from the street light. We have a 20-foot light pole and a 5-foot woman. Okay, now we need to define some variables. Okay, let's see. It doesn't really matter here. I'm going to use x's and y's. I guess it's probably the easiest way to do this, or the most basic way. Let's see. So we have, let's just say that is x, this distance here, and this distance is y. Okay. So we're going to try to figure out an equation that relates what's going on here, because we want to figure out how fast is y changing when x is a certain distance, 15 feet. Okay, and we're also told that that this distance right here, x, the distance from the streetlight, is changing at a rate of 8 feet per second. But since that 8 feet per second is getting closer to the street light, it's actually a negative 8 feet per second rate. Okay, if you're getting closer or lower to the origin, you're going to have a negative rate. So we could say this indicates to me that, according to how I have my variables listed here, that dx dt equals negative 8, we'll say, feet per second. Okay? Now, what we need to do is figure out a way to relate x and y. Okay? Now, whenever you see triangles, your first instinct should probably be Pythagorean theorem. Okay? However, that's not going to work in this instance, because we don't know anything about the hypotenuse. I mean, we could certainly use the Pythagorean theorem, but we would get an equation that would introduce another variable that we don't know about. So we need to figure out how to relate x and y with some of the known lengths already, 5 and 20. Now, whenever you have two triangles, as we do here, and very important, these are two similar triangles. Now, how do you know what's one way to tell if two triangles are similar? Well, in this case, we have two right triangles, and they both share this angle, theta. So if two corresponding angles of two triangles are congruent, that means actually all three angles are congruent, which that's one way to show that two triangles are similar. Now, what's one thing that's nice if two triangles are similar is that you can write some nice proportions. And one way you can write proportions is that the length, in this case, I'm going to be specific here, the base of the big triangle over, say, the height of the big triangle will be equal to the base of the small triangle divided by the height of the small triangle. What I mean by that is I can write this proportion. I can write x plus y, because that's the base of the big triangle, divided by the height of the big triangle, which is 20, will be the same ratio as the base of the small triangle, which is y, over the height of the big triangle, which is 5. And that's going to be how we get our related rates equation, because now we have an equation that relates x's and y's. Now, I probably want to clear the denominators, clean this up a little bit first. We can, let's say, cross multiply. If we cross multiply, or better yet, let's just multiply both sides by 20. That's easier. If we multiply both sides by 20 just to clear the denominators, like you're in algebra class all over again, multiplied by the least common multiple of the denominators of both sides, we get x plus y over here, and we get, let's see, that's 4y over here. Okay? And if we, combine like terms, we get x equals 3y. So now we actually have our a really simplified equation that relates x and y. And now let's take the derivative of both sides with respect to time. So the derivative of just a plain old x with respect to time is dx dt. The derivative of 3y with respect to time is just 3 dy dt. Okay, so now I know how everything's changing. Now I can start to plug in and solve for what I need. Now what I'm actually looking for here, what is the rate of change and the length of her shadow? So we want to know dy dt. So we need to solve for dy dt when dx dt is negative 8. All right, so dx dt, just simply plug in negative 8 equals 3 dy dt. And if we're solving for dy dt, a simple division by 3 on both sides does the trick for us. So negative 8 over 3. Now, what are the units here? That's going to be feet per second because we're talking about how the length of something changes. Feet per second is equal to dy dt. So her shadow is changing at a rate of negative 8 over 3 feet per second. Now, here's the kind of crazy thing. It's very counterintuitive, at least to me. It turns out that we didn't need this at all. And the reason we didn't need that at all is because when we differentiated both sides, there was no x left. There was a dx dt and dy dt. Those are the only variables we had. So it turns out that as long as the woman is walking at a constant rate, which is this negative 8 feet per second, as long as she is walking at a constant rate, the shadow is changing at a constant rate, which I remember a while back I was working on these problems and I was like, oh, I did not expect that result at all. I expected to be more dynamic, but it turns out the shadow is changing at a constant rate. So her distance between her and the light pole is changing at a constant rate, as is her shadow. Again, I thought that was interesting, a little counterintuitive. So there's the first part of our solution. Now the second question I think isn't too tough. At what rate is the tip of her shadow moving? So her tip of her shadow is way over here at this point. And how fast is the tip of that shadow moving? Well, her shadow is moving as x and y move together. So the tip of the shadow is moving at, she's moving at negative 8 feet per second plus negative 8 over 3 feet per second. So if we add those two rates together, that's how fast the tip of a shadow is moving. So let's see. We have negative 8 and negative 8 over 3. So a few common denominator situation here. Let's see. That would be negative 24 over 3. So negative 24 over 3 minus 8 over 3. If we add those two together, we get negative 32 over 3 feet per second. So that's when the tip is moving. Now we don't have a variable for that. It's just, maybe we could say, I don't know, x plus the rate of change of x plus y, maybe. Okay, and that is, so that's dx dt plus dy dt. That's the rate of her shadow moving. Dx dt plus dy dt. Okay, so there we are. That wasn't too bad, as long as you remember a few properties of similar triangles. So that's another one of those tools you need to have in your toolbox. Okay, similar triangles, Pythagorean theorem, the volume of a cube, volume of a triangle, or area of a triangle, volume of a sphere, all that kind of stuff. All those things have to come together to solve these. All right, let's up the ante a little bit. A little trig, okay? So trig usually freaks people out, but this one isn't too bad, I don't think. When I picked it out, it didn't look like it was going to be too difficult, but there's a whole big paragraph here, so let's see what's going on. It says, all right, the lighthouse problem. Lighthouse stands 400 meters off a straight shore, and a focus beam of light. A lighthouse stands 400 meters off a straight shore, and the focus beam of a light revolves around 4 times each minute. So that first sentence, note here. We have a beam of light that's revolving 4 times a minute. Okay, so keep that in the back of your mind. 4 times a minute. We have something going in a circular motion 4 times a minute. So that's talking to me immediately. Thetas and radians and things in that regard. So as shown in the figure, P is the point on the shore closest to the lighthouse, and Q is the point on the shore 200 meters from P. Oh, you know what? I changed the problem, and I forgot to change the text. So let's strike that. P is 175, okay? So let's ignore that. I changed it down here, but didn't change it down there. So 175 meters from P. What is the speed of the beam along the shore when it strikes Q? Describe how the speed of the beam along the shore varies when the distance between P and Q. Neglect the height of the lighthouse. All right, so let's see what we have going on here. I see, okay, we have a triangle. Now, I said earlier, when you see triangles, think Pythagorean theorem. If you have maybe 2 similar triangles, think proportions and similarity. But I left off one thing. If you have angles involved, you're probably going to be using trig. Now, here's the thing. We are talking about, we're given this, let's see, 4 times a minute is how fast this is revolving. So for me, that tells me that we have an angle here, theta. Theta in there, and theta is changing at a rate of, let's see, it revolves 4 times a minute. So if it revolved once a minute, that would be, you would go 2 pi radians per minute. But if it goes around twice, that's 4 pi radians per minute. So there's a theta in there that's changing at a rate of d theta over dt equals 4 pi radians, and we said per minute. So that first sentence tells me that we're talking about a theta changing at a rate of 4 pi radians per minute, because that's twice. That's 2 revolutions, not revolutions. Now I can't think of the word all of a sudden. 2 complete rotations per minute. 4 pi. Okay, because there's 2 pi in 1 rotation. So now we have a theta. We have a known set distance here, 500 feet off the shore. I think we can just simply say that tangent of theta equals opposite over adjacent. So that's going to be x over 500. Okay. So we have tan theta equals x over 500. So now we have a distance over here that's changing. Okay, we have this distance that's set, and we have related theta and x. So theta is changing and x is changing. Because this beam of light is sweeping the shore, and we want to know how fast it hits Q. How fast is x changing when it hits Q? Okay, so how we take the derivative of both sides with respect to t? Well, let's see. What's the derivative of tangent? It's secant squared. But we took the derivative of theta term with respect to t, so we have to multiply times d theta dt. Over here, well, what's the derivative? Don't do the quotient rule. You have a constant you can pull out, which is 1 over 500. The derivative of x would just be dx dt. So we have 1 over 500 times dx dt. Okay. Now let's see here. We have a secant squared theta. We have d theta dt. Well, we know what d theta dt is. That's just 4. We're solving for dx dt when the base of this triangle is 175 meters. Okay, so now we need, if we start plugging in here, we'll have secant squared theta times d theta dt, which is 4 pi, equals, actually let's just go ahead and multiply by 500 since we're solving for dx dt, times 500 equals dx dt. But now I have this pesky secant squared, and notice what I haven't used yet. I haven't used this fact, 175 meters distance between P and Q. So now what I can do is essentially just draw this other triangle. So let's look at this specific situation when I have a base of this triangle is a 175 and the height of the triangle is 500. Okay, theta goes right there, and I can just figure out what secant squared is. Okay. Conversely, I can figure out what theta is. So I guess I can do this one of two ways, actually. I can figure out what theta is. Okay, if tangent of theta equals opposite over adjacent, so 175 over 500, I could take the arctan of both sides and say theta equals arctan of 175 over 500. And I could plug in theta and do secant of theta. That's going to require, I mean, I don't know. I guess you're going to have to round at some point. That's fine. My first instinct, though, was to do it a different way. My first instinct, this is probably quicker, but to get the exact same answer, what I would do maybe is say, all right, well, there's theta. What's the hypotenuse here? Well, it's the square root of 175 squared plus 500 squared. Okay, so what's secant? Well, that's the reciprocal of cosine. So what's cosine? Cosine is what? Adjacent over hypotenuse? Okay, so if cosine is adjacent over hypotenuse, then secant will be the reciprocal of that. So we could say that secant theta equals hypotenuse, which is 175 squared plus 500 squared over adjacent, 500. Okay, that's secant. So secant squared is this. Okay, we can simplify that slightly, which is 175 squared plus 500 squared over 500 squared, which, rules of exponents here. You can square the top, square the bottom individually. So secant squared equals this. So then I can make that substitution, and now I don't have to round. Here I have to round. I mean, I'll get the same answer approximately. So I guess it depends on whether you're required to give an exact answer or if you're allowed to round. If you're allowed to round and you type that into your calculator, you'll get some decimal number. Like, let's see. Actually, I'm curious. What is arctan of 175 over 500? Let's see here. So inverse tan 175 divided by 500. It's approximately 0.3366 radians. All right. So there's your angle, but again, you have to round there. Here I have an exact answer. So now I can simply plug in, and I can say, all right, secant squared is this. So it's 175 squared plus 500 squared over 500 squared. And then we have times 4 pi times 500 equals dx dt. A little bit of simplifying here. We could cancel out 500 with one of those. since there's two on the bottom, two factors on the bottom, one on the top. So we could say an exact answer is 175 squared plus 500 squared over 500 times 4 pi equals dx dt. All right, so I guess what we can see what that answer is approximately. Just be careful with your calculator. 175 squared plus 500 squared times 4 times pi, and then divide by 500. Oh, it's 7,052.87577707, etc. Okay, international number. So that's an approximation. So it's about, if we round to the nearest whole number, about 7053. So we'll say approximately 7053 for a very rough approximation. Oh, and I forgot the units. Units, so we're talking about, okay, that's a linear distance. X is a linear distance, so what was it, meters? So let's not forget that. That is meters per what? Meters per minute. So meters per minute. Okay. So the trig throws a few people off, but just remember all your trig identities. This is just basic trig identities here. Tangent and secant. And again, there's two ways to do this second part where you're stuck with that secant squared business. You can either figure out what theta is using your inverse trig functions, or you can actually figure out what secant squared is by just simply setting up the triangle that uses that fact. If you set that triangle up, you're good to go. You have a little bit of algebra to work with, but it's no big deal. Okay, so that a little bit tougher. I admit, trig gets a little tougher. That's a pretty standard type problem. Like it seems like in every book there's a lighthouse problem. In every book there's usually a problem that talks about a patrol car, like an old school patrol car that had a rotating emergency light on the top, and how it's the emergency light sweeping the wall, and at what rate is that changing and stuff. So it's a pretty stereotypical related rates problem right here. All right, now let's move to the hardest one I have of the bunch. And again, this is pretty common too. I think I've seen this in several different textbooks. And it's tricky because of how the pool is shaped. It's kind of like a trapezoidal solid, or it is a trapezoidal solid. So it's kind of difficult at first to think about what's going on here. So let's see. We have a swimming pool, which is 50 meters long, 20 meters wide, and its depth decreases linearly along the length from 3 meters to 1 meter. It's initially empty and it's filled at a rate of 1 meter cubed per minute. How fast is the water level rising 250 minutes after the filling begins? Now, I'll admit that this took me a few minutes to figure out when I first, I took calculus years ago, then I went to grad school, went to grad school, got a PhD, got a master's, all that kind of stuff. Went back years later, started teaching Calc 1. I was like, man, I had to think about this for a minute. Because my instinct was to write a related rates equation for the entire pool. Now, the entire pool, you can write the volume of it, but it's a trapezoid. Think about turning the pool up vertically. The base would be a trapezoid times the height. But when you do that, okay, I'll just write it out just to show you. So a trapezoid is this shape right here. We have 1, we have 3 meters, and we have this. And we have the top of the pool like so. So that's a trapezoid. So if you wanted to talk about the volume of the pool, well, you have a 1 right there, you have a 3 right there. Okay. But the problem is, just the volume of the pool in general. Here's how you find the area of a trapezoid. It's, let's see if I remember right, it's 1/2 height. Now the height is the distance between the two parallel sides. So this was 50. So 1/2 50 times base 1 plus base 2. So 1 plus 3. So that's going to give you the area of the shape. All right? But if we're talking about related rates, we can't start plugging in variables yet. We have to let all those variables vary. You can't plug in. So we'd have to say something like this. You'd have to say 1/2, let's see, what we call that? L for length times base 1 plus base 2. So B1 plus B2. And now we have 3 variables to deal with, and we're kind of like, weirded out at that point because the rate is going to be changing at differently depending on where we are on the height of this pool. So I scratched this idea. That was all to say, kind of scratch that. But I do want to look at this picture. Think about this picture. So we're looking at a cross section of the pool. I'm going to draw this line here that separates this triangle, this trapezoid, into a triangle and a rectangle. Think about this. If you have water down here, do you think that little bit of water at first when you start filling the pool up, do you think the water level is rising faster or slower, say, than when the water level is up here almost full? Okay? And I hope you see where I'm going with this, is that when the water level is rising down here in this triangle portion, it's going to be rising at much faster than when, and at a completely different than when I get to this rectangle portion. Again, we're looking at a cross section of the pool. It's like we're standing right here looking into the pool if the side of the pool was all glass. Okay, so here the rate of change changes with height. The volume, the rate at which you're filling the pool up is changing with your height. But now let's make it up here to this rectangular area. Now we're just filling up a completely rectangular area, or volume, and when we fill it in, it's just going at the same rate. Okay, so we have a changing rate. The volume is changing, or excuse me, not the volume. I misspoke there. The depth is changing at a rate, variable rate, when we're inside this triangle, but the height is changing at a constant rate when we are in this rectangular area. So, depending on where we are in this diagram at 250 minutes, depends on how we solve this problem. Okay, because we have 2 different equations we just consider, 2 different volume equations. If we are talking about the volume on this at close to the bottom, that is, if we're talking about volume in this triangular area, well, we'll have what? It'll be 1/2 base times height times width, right? This is 2D. If we make it 3D, we'll have a width, and that'll be the volume down here. But if we're up here, and again, let me phrase this, be careful how I'm phrasing this. So this would describe the volume in that triangular area if we go to 3D. But if we're talking about volume up here, this I'm about to write here only really is true for how volume is changing. It's not really true for the volume of the entire pool. But how do you find the volume of just a rectangular solid? Well, it's just base times width times height. Okay, so it depends. If 250 minutes, if that puts me still down here, I have to work with this equation. But if that 250 minutes has already filled this bottom portion, that'll put me up here, and that will allow me to find how the height, the depth is changing. So we have two different equations we have to work on, and so the first step here is to figure out where are we at 250 minutes. At 250 minutes, have we filled up this triangular area, and now we're above in this rectangular area? Or at 250 minutes, are we still in the triangular area? My hunch is that we'll be in the triangular area still because it's easier otherwise, and they're not going to give us an easy problem to work. So let's see. How do we figure out where we are at 250 minutes? Well, at 250 minutes, we are filling the pool at 1 cubic meter per minute. So we have, at 250 minutes, we've put 250 cubic meters of water in the pool. So where would we be, let's see, at 250 cubic meters of water? How do we figure out if we're above or below that 3 meter mark? Well, let's see what the volume would be if you fill that entire triangular area with water. Well, it would be what, 3? So the volume here would be, if we filled that triangular area and then made it into 3D volume, it would be V equals what? C. That's 1/2. The base would be 3. So 1/2 base times height. The height of that triangle is 50. And the pool from our picture is 20 meters wide. So times 20. So what does that equal? Let's see. So 1/2 times 3 times 50 times 20. So if we fill up this portion of the pool, it's 1,500 cubic meters. Okay, but we've only put, at 250 minutes, we've only put 250 meters in, 250 cubic meters in. Okay, so that tells me that since I haven't passed that 1,500 meter mark, that I'm working in this triangular area. So I'm not worried about this equation. I'm working with this one. If I had passed that 1,500 meter mark, like let's say instead the question said, how fast is the water level rising 1,600 minutes after filling begins, I would use this equation because I would be past that 1,500 meter mark. But since I'm only at 250 cubic meters, I'm still operating in this little triangular area. So that tells me that this is the equation I'm working with. Okay, now let's see. Here's our equation. Now here's the problem. We have 3 variables: base, height, and width. One of those variables is not changing. Okay, think about this. The base. Okay, how do we have it listed here? Let me label our picture over here. So this is W. This is height. And I guess we'll just call that base. Okay, I guess that works. Okay, so let's think about this. Which one of those is not changing? Okay, think about this. Height is changing because we're putting more water in there. Base is changing because, think about this triangle. As the height increases, the other side of this triangle changes. If you have a height right there, there's your triangle. If you have a height right there, there's your triangle. If you have a height right there, there is your triangle. And each time your height is changed, your base is changing. That other side of your triangle is changing. So those two are changing. But what's not changing? W, the width of the pool. Even when your height changes, the width of the pool is not changing. So we could actually, in this case, we can plug in a 20 for W. So we can write, and get rid of one of our variables, we can write volume equals 1/2 times base times height times 20. Okay, so that gets us to volume equals 1/2 times 20, 10 times B times h. But we still have two variables. Okay, I want to get this, if I can, I want to get it to one variable, okay? Because otherwise I'd have to do a product rule with respect to t, which would be tedious, not impossible, but not ideal. We have to do it in other problems, but I think we can get around that here by looking at similar triangles again. Let me draw another cross section of a pool. Let me just exaggerate kind of what's going on. So here's essentially what we're dealing with. That's this bottom part of the pool. Okay, let's see. 3 meters to 1 meter. Let's see here. So that's, okay, first of all, if that's 1 meter and this entire side is 3 meters, then what would the side of this triangle be? Okay, if that's 1, that's 3. I think it'd have to be 2. Right? Because 3 is the entire right-hand side, 1 is that side. If we chop off 1 off the top, there's 2 on the bottom. Okay? So if 2 goes there, okay, 50 would be the top, let's say that of that entire triangle, be 250. Okay? Now let's say the water level is not yet to the top. So if the water level is not to the top, let's say it's right there. So let's draw some nice blue water in there. Okay. Well, now what can we say about this situation? Okay, well, let's just call that B and this H. Okay. So we have a 2 is the height of the, in this orientation. The height, let's not call it height, it's not height. 2 is this base of the big triangle. H is the base of the small triangle. 50 is the height of the big triangle, and B is the height of the small triangle. Okay, so what can we say here? We could say that, again, using similar triangles, since these are both right triangles, and they both share that angle, they're similar triangles, we could say that 50 over B, so the height of the big triangle over the height of the small triangle, is equal to the height, base of the big triangle over the base of the small triangle. And so we could say, let's see, 50 by cross multiplying, 50H equals to B. Now, I want to write my equation here for volume in terms of height only because that's what I'm looking for. I'm looking for how height is changing, how depth is changing, how height's changing. So I'm going to solve this for B so I can write this in terms of H only. And so I could write 50, dividing both sides by 2, 25H equals B. Okay, 25H equals B. Just divide both sides by 2. And now plug in over here. And so now I have an expression for volume, 10 times 25H, which is B, times H. And so volume equals what? 250H squared. So now I have an expression for volume, an equation for volume for any height, but this, again, this is only valid when we're in this triangular region. Okay? But now let's take now we're into one variable. Let's figure it out. So let's see, derivative with respect to t of both sides, we get dv dt equals, let's see, 2 times 250, so that's 500 h times dh dt. Okay, and so what are we solving for? Okay, well, let's see here. We're solving for how fast the water level is rising, so dH dt. dV dt, we know. dV dt is how fast the volume is changing. We're told that from the text. dV dt is 1 meter cubed per minute. So we could say 1 equals 500h times dH dt. Now I want to solve for dH dt. So we could say 1 divided by 500h equals dH dt. Well, now we're to a slight road bump because we've solved for dH dt, but this is still dependent on height. Okay, well, what can we do here? Well, what we can do is solve for h when volume equals, what, 250 minutes. We've pumped in 250 cubic meters per water. So if we could say off to the side, that 250 equals 250 h squared. So 1 equals h squared. So if we solve that, h equals plus or minus 1. And obviously the height's not -1, so we toss that solution out. And so we plug in the height at 250, after 250 minutes. We've pumped in 250 cubic meters of water. And the height of the pool is 1 meter. And so we get 1 over 500 equals dH dt. Let's not forget to label. So 1 over 500, let's see, dH dt, that's just a linear distance. So we would say that's meters per minute. So that is meters per minute. So the pool is rising at a rate of 1 divided by 500 meters per minute. Okay, that was a lot of work. That's definitely a tougher one. One of the harder ones we'll do in the class. And that's just because it takes a little bit of work to figure out what's going on. First of all, we're stuck with what equation do we use, or what are the equations? And if you start off thinking trapezoids, that doesn't work. Oh, we haven't answered the last question. How long will it take to fill the pool? How long will it take to fill the pool? Oh, well, that's not even really a calculus question. How long will it take to fill the pool? First of all, I need to figure out what the volume of the pool is. In fact, I just crossed that equation out. Let's not cross that equation out. The volume of the entire pool is what? The volume of the entire pool, if we use that my original formula here, 1/2 height times base 1 plus base 2 of the entire pool. That's let's see, 1/2 times height, which we said was 50, times base 1 plus base 2, which was like this, for because that's 2D. We need volume of the trapezoidal. So that's the volume of the trapezoid times 20 is the that's the area of the trapezoid times 20 gives you volume. So times 20 equals 2,000. So volume equals 2,000 meters cubed. So if the volume is 2,000 meters cubed, we're pumping in at 1 meter per minute. It's going to be 2,000 minutes. That's kind of weird. It's not even a calculus question. Oh well, cool. Yeah, so that's like I said, that's a tougher one. Obviously, on a test, don't expect one like this on a test. At least if you're in my class, this took me a while to explain it to you. For a test, think about what would be fair game for a test. Fair game for a test, maybe, maybe. But I can pretty much guarantee you that like the stuff that we first did, one of those is gonna be on the test. I can pretty much guarantee you that. Like one of these super easy ones, like this, that might even be too easy to put on the test, but maybe. I can pretty much guarantee you this like expanding cube type one, that would probably be on the test for sure. An expanding cube, an expanding circle, an expanding triangle, or whatever. Those basic, an expanding sphere. Those basic ones, I can pretty much guarantee you that something like that will be on the test. Something like this. And maybe even something like this, although that might be a little too easy, okay? Now, the other ones, they get harder, but you're going to have at least one or two of these on a test. They're going to be one of the easier to medium ones because you have other stuff. You have a test, you have to do a lot of other stuff on too, so it can't be the ones that take forever. But clearly, you have to know how to do the other ones for your homework. If you have any more questions, always feel free to email me on something. If you want more details about the stuff, check out my other video, my full-length lecture on related rates. You can find that on the channel. Don't hesitate to ask if you need any help. See you later.